Have you ever spent, I don't know, hours or maybe even days crafting the absolute perfect prompt for an AI,
Oh, yeah, we all have.
right? You meticulously outline all the rules, you provide these great examples, you hit enter, and, well, it works flawlessly. But then you plug that exact same prompt into a larger workflow, or maybe you pass it a slightly different document, and the whole system just completely falls apart.
It's infuriating. It feels like playing a digital game of whack-a-mole. You fix one error over here and suddenly three more pop up somewhere else.
Exactly. And if you've ever tried to build a complex workflow with these tools, you know exactly the frustration we're talking about today. You are constantly chasing edge cases.
And honestly, it has become a massive bottleneck for anyone who is trying to build like reliable production-ready systems right now.
Which brings us to the core mission of today's deep dive. We have this really fascinating stack of research in front of us today. It's anchored by a state-of-the-art paper titled FAPO. That stands for Fully Autonomous Prompt Optimization of Multi-Step LLM Pipelines.
Yeah, from the teams at Foundation AI over at Cisco Systems and Yale University.
Right. And this research really highlights this massive shift that is happening right under our feet. Because the era of simple human-led prompt engineering, just tweaking words in a text box, that era is ending.
It is. We are rapidly entering a phase where AI models are, well, they're autonomously diagnosing and rewriting and even restructuring their own operational pipelines.
Which is wild to think about.
It really is. I mean, we're witnessing a transition from humans giving instructions to the AI to AIs acting as the engineers of their own infrastructure.
Okay, let's unpack this. Because to really grasp why a system like FAPO is such a big deal, we probably first need to look at the reality of how modern large language models are actually used. Because the chatbot interface, right, that's just the surface level.
Yeah, exactly. For power users, the days of treating an AI like a single text box where you just type a question and get a poem, those days are largely over. In deep knowledge work, things like complex enterprise analytics or cybersecurity threat detection, these systems are deployed as multi-step pipelines.
So meaning a developer writes an orchestrating script that basically chains together a bunch of different AI actions.
Right. So a standard pipeline might start with a retrieval step, right? That searches a massive database, and then that feeds into a reasoning step that analyzes whatever raw data the first step found.
Got it.
And finally, a formatting step turns that analysis into a very strict data format, like, say, a JSON file, so that a traditional software program can actually read it and use it.
It's essentially a relay race.
That is a perfect way to visualize it.
You have these different runners handling different legs of the track. The first runner is your retrieval AI. They pass the baton to the reasoning AI, who then hands it off to the formatting AI for the final sprint.
Yeah, and just like in any relay race, a failure at one stage compromises the entire event.
Right.
If that first runner drops the baton, if your retrieval step fails to find the right document, it absolutely does not matter how fast your anchor leg is. You could give that final formatting AI the most beautifully optimized prompt in the world, but it is going to fail because, well, it was handed garbage data.
My immediate thought, though, is that we've seen optimization tools before. I mean, there are frameworks out there right now that automatically test and tweak prompts. Why couldn't those traditional optimizers, like, say, DSPy or GPA, just fix the drop baton?
That's a great question, and it comes down to a lack of granular visibility. You see, traditional optimization tools are generally designed to optimize prompts inside a fixed, unchangeable pipeline.
Meaning the structure is locked in.
Exactly. They use algorithms to tweak the text of your instructions over and over to see what gets a better final score, but they don't fundamentally change the structure of the race itself. FAPO approaches the problem completely differently by treating the pipeline as a transparent, inspectable workflow.
So it's not just looking at the final time on the stopwatch.
No, it reviews the tape of the entire race to find the exact moment the baton hit the ground.
Oh, wow. So if previous tools were just trying to give the runners better shoes, FAPO is actually analyzing the biomechanics of the runners to figure out why they stumbled, and then deciding if we need to change the race strategy entirely.
That's a really great analogy.
So let's get inside the FAPO engine to see how it pulls that off. Because from what I understand, this isn't just a new language model. It's a full framework, and the orchestrator running it is actually Anthropic's Claude code.
Yeah, that's right. We literally have Claude Code acting as the chief mechanic here, actively diagnosing and fixing other AI models like GPT-4 and Gemma.
Which is just so cool. So how does this mechanic actually work?
What's fascinating here is the rigorous, almost scientific loop that FAPO runs to execute these fixes. It represents the entire pipeline as a stateful graph, which is really just a technical way of saying it can track the inputs and outputs of every single node at every single step of the workflow.
Right, and it does this in 5 distinct stages, right?
Yeah.
So if it's acting as a mechanic, I imagine stage 1 is just, turning the key, watching the engine run on a test track, and waiting for smoke to appear.
Pretty much. That is the evaluate stage. FAPO runs the current workflow on a set of training cases. It records the final answers and the overall scores, but crucially, it captures the intermediate outputs from every single step along the way.
So it's gathering the raw evidence of the failure.
Exactly, which means stage 2 has to be sifting through that evidence to find the root cause.
Okay, so how does it do that?
Well, we call that the attribute stage, and it is where the heavy lifting happens. A specialized sub-agent diagnoses the failures by looking at those intermediate step artifacts. It doesn't just flag a bad final score, it actually asks, why did this fail?
Like, did the search query return empty results?
Right. Or did the reasoning model hallucinate a fake fact? Did the formatting model get too verbose and break the required structure? It categorizes the specific error.
Okay, so from there, it must isolate the biggest bottleneck and suggest a fix, which would be stage 3.
Yeah, the proposed stage. Based on that granular diagnosis, FAPO suggests exactly one scope change to address the most dominant failure. It is incredibly methodical about this.
Now, my concern here, though, is that autonomous algorithms, well, they love to cheat.
Oh, absolutely.
We've all seen the stories where AI plays a video game and figures out that the easiest way to win is to just pause the game indefinitely so it never loses, or it just rewrites the scoring rules entirely. If FAPO is constantly rewriting its own code to chase a higher score, how do we know it isn't just overfitting to the test or secretly memorizing the answers?
The researchers anticipated that exact danger. Because you're right, unconstrained AI will absolutely find the path of least resistance. That's why stage 4 is review. An independent, entirely separate sub-agent reviews the proposed change. It checks for safety and ensures there is no data leakage.
Meaning it guarantees the optimizer hasn't accidentally peaked at the final exam.
Precisely. FAPO enforces this through strict split access control. The optimizing agent that's making the changes only ever sees the training cases. It is completely blind to the final validation and test sets.
Oh, that's smart.
Yeah, it only gets aggregate performance scores, never the individual answers. Furthermore, the human developer defines a strict tenant playbook dictating exactly what files FAPO is allowed to touch.
Got it. And then I assume it just runs a comparison to see if the fix actually improved the aggregate score, which would be the 5th and final stage.
That's the compare stage. It either accepts or rejects the change based on that aggregate validation score.
It's a pretty airtight loop. Evaluate, attribute, propose, review, compare. Also, I read in the source material that every attempt FAPO makes is actually saved as a brand new trackable file. So it leaves an audit trail. It's not just overwriting your master file in the dark.
No, and that variant immutability is crucial for developers who need to actually trust the system in an enterprise setting.
Okay, but here's where it gets really interesting. This loop makes total sense for tweaking a prompt. But what happens when changing the text instructions just isn't enough? Like, what happens when the underlying process is fundamentally broken?
And that brings us to the escalation protocol, which is arguably the most powerful mechanism in the entire framework. FAPO operates on a core rule: prefer the smallest useful change.
Makes sense. Editing text is fast and cheap.
Exactly. Because editing a text prompt is cheap, it always tries to fix the problem with better instructions first.
But if the attribution agent realizes the runner is physically incapable of making the distance, say, the retrieval search is just searching the wrong database, or maybe it isn't looking deep enough, a better prompt won't save you.
Right. And if the human-defined playbook allows for it, FAPO will stop tweaking text and escalate. It will alter the parameters of the chain, or even completely rewrite the architecture of the pipeline itself.
So it effectively fires the runner and hires a new one, or it changes the layout of the track entirely.
Yes. And the proof of this in the paper is staggering. The researchers tested FAPO on a notoriously difficult fact verification benchmark called Hover. The AI essentially has to jump between multiple complex documents to verify a convoluted claim. It requires really deep, multi-hop reasoning.
And the baseline setup for that test was a standard 3-hop retrieval chain, right?
Yeah. It would search a document, find a clue, search a second document, find another clue, and search a third.
But when FAPO ran its diagnostic loop, it realized those 3 hops just weren't retrieving enough context to answer the questions. So, entirely autonomously, FAPO rewrote the pipeline's code to extend the retrieval chain to 4 and then 5 hops.
And on top of that, it added a multi-query search node to gather broader context right at the start.
The resulting performance jump was massive, wasn't it?
Unbelievable. A traditional prompt optimizer like GPA scored around 31.7% on this task. By restructuring the pipeline, FAPO pushed the system's mean score up to nearly 83.8%.
Wow, over 80%.
It proved definitively that prompt-only optimization has a hard ceiling. If the architecture is flawed, you have to change the architecture.
And it did something even more creative on another test, the IF bench instruction following test. This benchmark was measuring whether the AI could stick to incredibly strict, complex formatting constraints.
Which, as any developer knows, LLMs are notoriously bad at outputting perfect syntax. They love to add conversational filler like, here is your JSON output, which instantly breaks the downstream software that is just waiting for raw data.
Right. And FAPO realized that relying on a language model to perfectly format its output every single time was just a losing battle. So it escalated again.
Exactly. Instead of begging the AI in the prompt to be better at formatting, FAPO autonomously added deterministic post-processing nodes to the pipeline.
Wait, so it wrote its own standard Python code?
Yes. It wrote Python scripts to catch the LLM's output, strip away the conversational filler, and physically force the data into the correct brackets before handing it in.
That is incredible. FAPO recognized the inherent limitations of a language model and just built a traditional software safety net to catch the errors.
And by building those post-processing nodes, it absolutely dominated the formatting benchmarks. On IFBench, it won all 6 comparisons with a mean gain of over 33 percentage points.
Going back to our analogy, it isn't just rewriting the factory's instruction manual anymore. It is autonomously installing new conveyor belts and building automated quality control checkpoints to guarantee the final product is perfect.
It's a complete paradigm shift.
But I have to ask, if it's willing to aggressively rewrite the whole factory floor, where does this strategy fail? What happens when it hits a problem it just can't solve? Let's look at the overall scorecard.
Sure. So across a big picture 6 benchmarks, 3 different task models, FAPO beat the GPA baseline in 15 out of 18 comparisons. It had a mean gain of 14.1 percentage points. Even on tasks restricted to prompt-only edits, it won 9 out of 12 times.
But it did lose somewhere, right? Transparency is key here.
It did. It stumbled on the AIM benchmark, which is a highly complex competition-style math test. GPA actually led there, though the results were pretty close to the noise range.
Which is fascinating to me because math is usually considered so objective and straightforward for computers. Why did an autonomous optimizer struggle there?
It comes back to the vastness of the problem space. Complex mathematical reasoning has a nearly infinite number of edge cases. When you have a relatively small number of training examples, a highly reactive system like FAPO can actually become a victim of its own efficiency.
Ah, so it overfits.
Exactly. It hyper-optimizes for the specific types of math problems it sees in the training set, creating a brittle pipeline that basically shatters when it encounters a truly novel problem on the final test.
So it builds a highly specialized tool for algebra and then gets completely blindsided when handed a geometry question.
That's exactly it. The performance drop was small, but it really serves as a reminder that autonomous optimization is not a magic bullet for every single domain just yet.
Speaking of performance drops, I have to bring up this bizarre anomaly from the baseline testing. I saw in the data that an older model GPT 4.1 mini was consistently beating the newer, theoretically much smarter reasoning model, GPT 5.4 mini.
Yeah, that was wild.
On paper, the newer reasoning model should have crushed the older version. What happened?
This is actually one of the most revealing findings in the entire stack of research. And it highlights a really critical misunderstanding about how these new reasoning models operate. It had absolutely nothing to do with the newer model's intelligence and everything to do with the constraint called the token budget.
Okay, a token budget.
Right. Both models were given a strict limit of 16,000 tokens per generation. Think of a token budget as the amount of breath you are allowed to take before you have to stop speaking.
So you have roughly 16,000 words, give or take, to make your point.
Exactly. Now, for the older model, that 16,000 token limit only applied to its visible output, the final answer it actually types onto the screen. But the newer model is a reasoning model. It engages in a massive amount of hidden thinking, before it ever outputs a single visible word.
Oh, I see where this is going.
Yeah, the system provider structured the token limit as a shared budget, meaning those 16,000 tokens had to cover both the hidden reasoning and the visible output.
Oh, so it was literally thinking so deeply about the problem that it ran out of breath before it could actually state the
But
answer.
exactly, it was exhausting its entire token budget on complex hidden calculations. When it finally arrived at the solution and tried to format the output, it had 0 tokens left.
That is hilarious, but also terrible for a pipeline.
The data logs showed that on complex math tests, the NUA model was spitting out median outputs of just 78 tokens. They were these short, malformed fragments that instantly failed the strict formatting requirements.
It was suffocating under the constraints of the test. And FAPO's step-by-step diagnostic loop is what provided the hard evidence to actually prove it. The logs showed that to make the newer reasoning model competitive, developers had to raise the budget to 24,000 or even 28,000 tokens.
Which is a huge insight for developers.
So what does this all mean for us? We've talked a lot about academic benchmarks, math tests, and fact-checking. How does an autonomous pipeline mechanic apply to the messy, chaotic tasks that industries deal with every single day?
To answer that, the researchers deployed FAPO on a real-world cybersecurity task called CTI Bench RCM.
And this was a tough one, right?
Very. The challenge was to take dense, highly technical descriptions of software vulnerabilities, these CVEs, and map them to their exact root cause categories. There are 263 potential classes, and it is a deeply nuanced classification task that human security professionals usually spend hours doing.
But for this specific deployment, the researchers tied one of FAPO's hands behind its back. Because of strict security protocols in this specific environment, it wasn't allowed to use the escalation protocol. No rewriting the pipeline, no adding Python nodes. It was restricted strictly to prompt optimization.
Right. And yet, even with those severe restrictions, FAPO improved test accuracy across the board. It boosted the performance of massive general models by 4 percentage points, and it significantly improved specialized, smaller security models by over 7 points.
But the actual text of the prompts it generated to get those boosts, that is where I found this brilliant irony in the paper.
Oh, the GPT-5 crowd.
Yes, when FAPO was tasked with optimizing the massive, highly capable GPT-5 model, it analyzed the failures and generated a massive 23-line prompt. It was incredibly dense with highly specific rules, basically telling the model, if you see a buffer overflow, categorize it as CWE 787, but never CWE 121. It basically handed this giant model a dense textbook of edge cases to read before every single task.
Which works because a model of that immense size has the parameter count and the capacity to digest, hold, and apply all of those nuanced rules simultaneously without losing focus.
Right. But then FAPO turned around to optimize a much smaller 8 billion parameter model, the Foundation Sec 8B Instruct model, for the exact same task. Human intuition would say, well, a smaller, less capable model needs even more help, so we should give it an even longer list of rules to guide it. But FAPO's diagnostic loop discovered the exact opposite.
It realized that feeding a massive list of rules to the smaller model was actually overwhelming its capacity. The smaller model was getting so tangled in the instructions that it was failing to extract the format correctly.
So FAPO ruthlessly cut the prompt down. The highly optimized instruction manual for the smaller model was literally reduced to just 2 sentences.
It's amazing. And if we connect this to the bigger picture, this is perhaps the most profound takeaway from the entire research paper. It definitively proves that there is no such thing as a universal perfect prompt.
It's a myth.
Totally. An optimized prompt is entirely relative. It depends on the specific model's parameter size, its unique reasoning style, its token budget, and its structural weaknesses. A prompt that acts as a huge performance multiplier for a massive model will actively degrade the performance of a smaller one.
Wow. So FAPO doesn't just search for good words. It molds the instructions to perfectly fit the psychological profile of the specific AI it is managing.
It is bespoke tailoring for code.
So to pull all of this together, we have traversed quite a landscape today. We started with the universal frustration of humans blindly tweaking text prompts, hoping for just a slightly better output. And we arrived at a system that uses evidence-based attribution to isolate exactly where a multi-step workflow breaks down.
Yeah, using Claude Code, FAPO autonomously tailors prompts to the specific quirks of individual models.
And when a better prompt isn't enough, it escalates. It writes Python scripts, builds new search nodes, and completely rearranges the architectural factory floor to guarantee the final product hits the mark.
It really represents a massive leap forward in the reliability of autonomous systems. I mean, FAPO demonstrates that AI can rigorously diagnose and fix its own architectural flaws to satisfy a human-defined score.
What?
But as these pipelines become increasingly complex, as systems like FAPO autonomously add multi-hop structures, change parameters, and invent data flows that we didn't explicitly design, this raises a really important question for you to mull over.
Where does this lead us?
Exactly. At what point do these autonomous architectural optimizations become so intricate and so deeply tailored to the obscure quirks of a specific model that we as humans no longer understand how the pipeline is arriving at the right answer?
That's a little terrifying.
If the final score is perfect, but the factory floor has been rearranged into a labyrinth that only the AI understands, are we still in control of the process, or have we surrendered everything just to guarantee the outcome?
The diagnostic machine isn't just broken anymore. The AI has built a completely new X-ray machine that we don't even have the schematics for. You might have the perfect relay team, but you no longer recognize the track they're running on. Definitely something to think about the next time you're tempted to just ask an AI to fix your workflow for you.